Okay, so in this section, we're going to look at trust no one options. And typically I lead into this with these 4 questions where I'd ask you to think and discuss with a partner, somebody near you, about whether or not it's possible for service providers to first search encrypted databases, to second search an encrypted database and not know what the results are, and then third search an encrypted database, not know what the results are, or even the search terms themselves, and then fourth, to do all of those things at Google scale. And to answer yes or no, is it possible for each of these 4 increasingly complicated scenarios, is it possible to even begin doing this? And it is worth pausing this video, thinking for a moment about everything that we've talked about thus far with cloud providers and determining whether or not you can answer yes for whether or not it's possible to do each of these things in each of these 4 scenarios. So go ahead and pause the video and then think about it on your own. We'll come back and discuss it after you. Well, I mean, we don't have to come back and discuss it. You can just unpause the video, and then you'll see kind of where we're going. The answer is basically, yeah. Like, you can actually kind of do this using trust no one implementations. All 4 of those scenarios are possible. And we're going to look at this as a way to identify how this is possible, right? There are 2 different implementations that we'll look at, LastPass and Boxcryptor. They're both examples that are in the textbook, and these are graphs from the textbook. I'm just going to be walking through them to show you how this sort of stuff works. The main thing that you want to look at here is actually the server line down at the bottom, okay? Because this is really where the magic happens, or at least the important piece happens. The server never has access to the key that's needed to do decryption, okay? The server never has access to the key that's needed to do decryption. So if you're looking at LastPass, LastPass is one of those password manager, password replacement systems where you are encrypting all of your passwords into a single file or to a single database, and then when you need to log into something, you can get the appropriate entry from the database and use it for whatever client you're interested in using. Or whatever site you're trying to log into. So the way this typically works, the user is going to enter their username and master password in the client itself. This is you, the user, doing the entry. The client then does the hashing and salting of the master password, and at that point is able to provide all of this information to the server, which is authenticating the user. Now, separately from this line right here, you can see the user is actually also getting the master password decryption key from the client, right? The client is providing this decryption key. There's never a communication with the server to get the key. And all the server is doing is providing the encrypted database file from the LastPass server to the local LastPass client. And at this point, the key is used to create or at least provide access to the actual password in the database. Okay, so this is a trust no one implementation. You don't have to trust the server at all. The only person who ever has access to this stuff is the user and the client, meaning the computer the user is controlling in order to do this decryption. And the fact that the server never has access to the key, this decryption key, that's actually the most critical point to be made. In Boxcryptor, we have a similar approach. In this case, the provider only ever has access to encrypted data and never has access to the key to decrypt it as well. But we're doing something in a slightly different way because we're both adding an encrypted file to the provider and then retrieving an encrypted file from the provider. So they're 2 entirely separate scenarios here. In the first scenario, the user is adding the file using Boxcryptor encryption to cloud storage. Now they're adding the file to their local client, which is generating the file key for this file and saving the file key locally, right? And then encrypting that local file key so that both the file and the encrypted key are provided in an encrypted format to the storage provider. So now you have the encrypted file and the encrypted file key both in the service provider. And this encryption key is actually randomized by the client, right? So the client is generating a random file key for the client, for the file that the user is intending to upload. And then when you're looking on the retrieval side, say the user now needs to access whatever this file was that they provided to Boxcryptor, you just make a request, and all you have to do is provide the file descriptor. The client will actually do the encryption. The file will actually do the request for the encrypted file and file key from the provider, which can then be provided, assuming this authentication piece has already happened. Once that encrypted file key and the encrypted file are provided, the client can actually decrypt the file key using the user's private key, right, which is provided only locally to this client, and also decrypt the file key, which then allows the user to do the file encryption. Now, the big difference between LastPass, which is what we just discussed previously, and Boxcryptor is in the LastPass implementation, the only thing that's actually necessary is the username and the master password, which the user can remember. So the user can basically handle all of this stuff in their own memory. In the Boxcryptor scenario, which is kind of like a competitor to Dropbox where everything is encrypted, it's very similar to SpiderOak. The user is not going to be able to remember every possible file key that they have for every possible file that they want to upload, right? This is going to have a client that maintains some memory that the user is never going to have in their head. So the client is much, much more critical in the Boxcryptor scenario than it is in the LastPass scenario. And this is what makes it scalable. This is why you'd be able to do this for hundreds or thousands or possibly tens of thousands of files on the client side, because the client can do all of that memory for you. But you're not going to be able to just go from one system to another very easily with Boxcryptor, because the actual client does do a lot more memory than you would see in the LastPass implementation. So in essence, this is showing you like the simple version of like, is this possible? This is questions, I think, essentially 1 through 3 on the previous slide. Let's see here. Yep, it's basically 1 through 3, because you're not going to know what the actual encrypted file is, the contents of the encrypted file. And then this is kind of showing you all of the rest of them, like the scalability piece. The last thing I'll say about this is these two examples are not particularly Google-like, but you can actually do this, an encrypted search over encrypted data using an encrypted search term that the server would not know anything about, basically by using all of the primitives that we see demonstrated here. All of that can happen using the primitives that we see here. It's actually easier to scale using something called homomorphic encryption, which is managed and maintained. Mostly, the largest implementation of this is managed and maintained mostly by IBM. Okay, let's talk a little bit about data loss prevention, because this is very much tied to cloud environments. Now, I've bolded here the idea, the one area where I would want to, if I were in charge of this, the most expensive option is infrastructure as a service. But this is the one option that I would actually want. The first option here would actually be my runner-up. It's a little bit tricky to figure out what the best data loss prevention strategy is for most environments, because data loss prevention depends on the actual value of the data. And most organizations have kind of their own little spin on what makes data valuable to them. But for intellectual property based organizations, think Sony, think any of the Hollywood productions, data loss prevention may be the number one concern you have. Like, the worst case scenario is that you spend several $100 million amping up the release of a movie for a particular opening weekend, and then 2 weeks before it's supposed to open, somebody's able to get access to the digital files that make up an early cut of the movie or a director's cut of the movie prior to the actual theatrical release. So there's a lot of organizations where intellectual property is a critical element of their strategy, and in those organizations, data loss prevention makes a huge difference in terms of whether or not you're going to be profitable. And for those organizations, I do actually think in infrastructure as a service environment, it's very important to have some kind of a data loss prevention server that serves as a proxy between user systems and other corporate cloud servers, so that you don't have any of these leaks. It's very difficult to do this sort of thing, because it's very difficult to describe this sort of thing in the general sense, because every organization has a different set of things that are actually important for intellectual property purposes. The other key piece, though, is all of this is more difficult in a cloud environment than it is for on-premises servers. And similarly, all of this is much more difficult in an on-premises client-server model than it would be for an on-premises individual siloed air-gapped computer model. Right now, at some point, convenience is going to make things more beneficial to have a cloud environment, whether it's an on-premises cloud environment, a local network for your organization, or even a global cloud environment, true cloud computing environment. It just depends on the organization. Understand that it's a trade-off, though. Data loss prevention, especially when you're moving into the cloud, is an entirely different scenario than if you're just doing air-gapped machines on individual systems. So you want to make sure that whatever system whatever approach you're using, your organization is actually positioned to manage. All right, cloud application security. The last big thing that I wanted to say about some of the cloud provider stuff is these are all shared resources, and the two big problems with that are the actual access to the resource themselves, so like logging into a shared cloud service, or the mechanisms that are explicitly used to share access to resources, so APIs. In the first case, sharing a system where you and I may both have actual login accounts that map to the same physical server, but that physical server is hosting multiple virtualized servers. There's a barrier there. That hypervisor barrier exists and can be attacked. It's actually a surface area for attack. And this is one of the reasons why Meltdown and Spectre were such serious bugs, because they provided huge openings in shared service environments where, as long as you're on the same physical machine, you'd be able to get access. And no one really knows exactly what physical machine they're going to, because they're all logging into something that is a virtual machine. And you never know who your neighbors are in that kind of a scenario. They could be competitors. They could be just random people. It doesn't really, there's no easy way to tell exactly what that would be. So you kind of have to assume the worst case scenario and move from there. It's a little bit difficult to come up with a definitive way of identifying that, unless you're actually doing the cloud provider. Like if you work for Amazon or Google, obviously they would know how the physical machines map to virtual machines. For APIs, the problem is a little bit different. Cloud vendors have this very long and pathetic history of releasing bad APIs, or APIs that are broken in some way and provide more access than they need to. API design is actually kind of difficult, and it's the kind of thing that is sort of recently being recognized as an area where we need to devote some real serious thinking and resources to designing good APIs. But the main thing here is actually that the insecurity of the API is tied to weaknesses in underlying crypto libraries, for now, at least. The best example of this is something like the goToFail bug, where a broken SSL library makes it easier for someone to get access to an API that they shouldn't have had access to. That's slightly separate from what I think is eventually going to be the bigger problem, designing an API to provide data without providing too much data, right? You want to provide access to data. That's why you would have an API in the first place. But you don't want to provide too much access or allow for too many queries over a small period of time. If you remember when we talked about differential privacy and some of the concerns there, the differential has to be time associated, not necessarily like limited, but you want to know what the time period is that you're trying to protect against, because the more time you give somebody to continually repeat queries, the more likely it is that they will be able to uncover some sort of differential that gives them access to some of the underlying data. Same basic problem happens in security. The more access that you give in terms of the number of queries per week, day, month, hour, whatever it might be, the more likely it is that somebody's going to be able to find a security weakness in your system. So if you're only allowed one query, hard to figure out security problems. If you're allowed two queries, maybe it's a little bit easier, but it's still pretty hard. But if we're talking literally thousands over a period of days, it may be impossible for you to create an API, even a good API, that would be perfectly secure against those environments. And I don't think these are particularly shocking application security concerns. The notion that, hey, we're using shared resources and an API that provides access to data may be challenging to design well. But they're worth consideration when you're thinking about moving into the cloud, because they don't exist at all in a traditional environment. You're not sharing resources. You just have one server for your organization in a traditional environment. And you don't necessarily have to worry about insecure APIs, because if your organization isn't relying on APIs that are publicly facing, you don't have to worry about those controls. It's only available internally. Now there is one big caveat with this, and that is insider threats, right? In cloud application security, you're sort of forced to treat everybody as an insider, including the general public, your traditional external hackers, because the cloud is making available access points that would otherwise be internally handled. And we all recognize insider threat as one of the biggest security concerns in the business. And so this may actually help in some sense, because you're formally forced to think about it. There's no option not to think about the insider threat, because each of these things is now public. It's no longer an insider threat. It's actually a legitimate outsider threat as well. So good organizations, this isn't really much of a problem, but some organizations that think of security as important but external, they may actually see improved security mechanisms simply because now they're actually thinking about who might have access to some of these resources, or how could this information be misused in an API that we've set up.